So we'll start today the first introductory part into the course, and the starting point today, inshallah, is going to be from the very beginning. What's a communication system? So what does it contain? And then we will go after that into what's the focus of this course on a particular communication system, and then we will go quickly over necessary information that you have to have as a background in order to be able to go through the course successfully, inshallah. And I will just mention some organizational stuff at the end, inshallah. Okay, so if you have taken any courses in communication before, you probably have been exposed to the main component of a modern communication system. So you have some source, you have an analog front end, attached to the analog front end is an antenna. Okay, and the signal comes out from the antenna, goes to the free space. Typically, we are more concerned with wireless communication systems. Okay, the receiver chain is the opposite of this. So in the receiver chain, you have an antenna, which is receiving some signal, and then whatever comes from the antenna goes through an analog front end as well, but that's on the receiver side, and then it goes through a digital baseband, and finally whatever is your receiver. So if, for example, we said the transmitter, the source was a microphone, here is going to be a sink, and maybe this is going to be a speaker, for example, so you can listen to the voice of the person on the other side trying to transmit your signal. Okay. As far as this course is concerned, we are more focused on this part only, both from the transmitter and the receiver side. So the analog front end with the antenna. I know some of you took antennas a little bit in electromagnetics. Many of you didn't take antennas at all. So I'm going to touch a little bit about the antenna design as part of this course. So we'll discuss that when it comes to be in order within the course schedule. The digital baseband part is more related to digital communication. I see here, for example, BBSK, 4PSK, all these QAM, all these things that were mentioned to you, whether in your communication or digital communication course, are more concerned of what happens in the digital domain of the signal. Some of the wireless communication courses, for example, studies the link between those two, the transmit antenna and the receive antenna, with some methods that are used in the digital baseband to overcome the challenges that exist in the wireless communication system. And part of the wireless communication studies something called the protocols. So how do you connect two nodes in cellular system as opposed to in Wi-Fi, as opposed to this, as opposed to that. So that's, again, most of what you studied so far has not been focused on how you implement this part, which is essential of any communication system. Okay? Whether your communication system is a pure analog system, so it will only contain this part, directly connected to the source and the sink, or it's a digital communication system, which is more than 95% of nowadays communication, where it will contain the digital baseband part in addition to the analog front end as well. Okay? Now, since our focus is going to be only on those parts, and since when we look at the communication system from this perspective, we can completely forget about what's happening here in the digital domain. So as far as we are concerned in this course, this is how a communication system will look for us. So we have a source. Let's say in this case, we have a microphone. Okay, and this is connected to a transmitter, call that TX, and then the transmitter is connected to an antenna sending our signal out. Okay, and that transmitter For us, it's just the analog front end part. We don't really care about what happens in the digital domain at all. Okay? Similarly, the receiver side is going to be an antenna connected to a block. We call that the receiver, RX. And then it's connected to some sink. Maybe because we put a microphone there, then we can put a speaker, for example. And then the signal comes to the antenna. It goes through our receiver until we can listen to it. Now, if this is the way that we represent our communication system, the question that comes here is, what are the challenges, what are the requirements that we need to attain in our signal in order for it to be successfully transmitted from the source, the microphone over there, until you listen to the exact same voice representation at the speaker side here. One thing that you know about, whether from your electromagnetics course or from your other communication courses, is that there is a loss of power when it goes from the transmitter until it reaches the receiver. There is a lot of power losses in that link, whether it's a wireless link or even in a wired link, there are losses as well, not as much as in the wireless case, but there are losses. So if you know that the power is going to be lost, and from your knowledge of electronics, you need a certain minimum level for any signal to be actually detectable, then first thing that comes in mind that probably I need some kind of amplification. I need to amplify my signal, right? And probably I need to do this both sides, at the transmitter and at the receiver as well, right? Okay. It looks like this is the only thing that we need, but reality is no, this is not the only thing that we need. There are many other challenges that comes into the picture that will require us to have really many more components in that transmitter and receiver. In reality, the requirements are put so that the issues of the communication system are mostly handled by adding more components to the transmitter. Okay? But the problem is, those components, they change the nature of my signal. And eventually, to be able to listen to the same voice, I have to counter the effect of those components. So that's why also the receiver is not going to be a simple amplifier. I will have to put another counter component for each one that I put in the transmitter. I'll give you a couple of examples of the challenges. One of them was for example, the amplification thing. The other example to take into account, remember from your physics or electromagnetics or whatever, there is a general concept that says that the dimensions of an antenna are typically proportional to the wavelength that you are operating on. Okay. Sometimes you say lambda over 2, lambda over 4, right? But it is proportional eventually to the wavelength that you are operating on. So let's look at this example that we have here. I'm talking about voice signal. Voice is typically, so if I assume that my signal is voice is typically between 3 hertz up to 3 kilohertz. Sometimes they take it up to 30 if it includes music and stuff like that. So it can go all the way up to 30 kilohertz, right? That's the typical frequency range of voice that we can hear as human beings. So the signal that you are dealing with is between 3 hertz up to 30 kilohertz. If I say that I'm going to take my nominal frequency of operation as the middle point, roughly this middle point is going to be around 15 kilohertz, right? So I am operating at around 15 kilohertz as a frequency. This is F, okay? So if this is my F, what's my nominal operating wavelength?
No, not UP over. UP over.
Yeah. In free space, C over F, okay? What's C? The free space propagation speed of light, right? So that's 3 times typically 10 to the power 8. And this guy is 15 times 10 to the power 3. So what's the nominal value of my lambda? We are talking about lambda is in the range of 10 to the power 4 approximately. Okay? Plus or minus, right? That's my typical nominal operating wavelength, which means that I'm looking at an antenna dimensionality, which is about 10 kilometers, right? Imagine your antenna is 10 kilometers, right? You cannot do that, right? So there is a challenge here that I can't really work with low frequencies. But the nature of my signal is low frequency. What can I do? I have to bring it up in frequency. I have to increase the frequency of that signal, right? So that probably introduces some kind of another component here, which is gonna do modulation. Since I already changed the nature of the signal, I brought it to a different frequency range, but eventually I want here to listen to the original signal, the actual voice. So I have to bring it back down. So once I added a modulation at the transmitter side, I have to add a demodulation corresponding component at the receiver side. And things will go like that. So there are other challenges. To address them, you need to add something in the transmitter, but because that is going to change the nature of the signal, you need to add something to counter that in the receiver, right? In this course, we will learn those challenges, what to do in terms of components to counter the challenge, how to design those components, and also how to design their reverse operation ones at the receiver side. Okay, so that's kind of the scope of the course. Any questions so far? No questions, things are straightforward, right? Now, having that said, there are some background information which we really need in order to be able to carry this operation forward, okay? So I was discussing those background information one by one. So the first thing is signal representation. In time and frequency, right? That's a background that you have studied in your signals and systems, right? I have my voice, for example, right, which is a signal. Typically, we understand it as human beings in time domain. That's what we typically tend to intuitively deal with when we deal with signals, right? So my voice, if I represent that as a function of time, as I speak louder voice, I'm going to end up with some higher amplitude. I lower my voice volume, some lower amplitude, and so on. So some variations as I speak or as you speak, right? And it is a variation with respect to time. Okay. So these are different amplitudes versus time. However, when we deal with a communication system, we've just seen that I actually want to take that, figure out first of all, what is the frequency range that it occupies so that I can design my antenna, right? Not only that, I found out that when I figured out its frequency range, I ended up saying, oh, it's not suitable for my antenna design, I have to bring it up in frequency. So in all these cases, when I was trying to figure out what's the frequency range, or what do I need to do with the signal so that it can be transmitted, or what can I do so that it can be transmitted with efficient antenna design, I wanted to look at the signal from a different perspective. I didn't want really to look at it from the time domain, how it varies with respect to time. It tells me nothing about what's the upper frequency, what's the lower frequency, and so on. I wanted actually to look from an orthogonal direction, which is the frequency representation, right? That frequency representation, you learned it in your signals and systems course, and you started by the concept that tells you about those frequency representations, which says that for any periodic signal, for example, a signal, let's take a general signal. It looks like this. Okay, so this is not even parts of sinusoid. It's kind of a triangle, but smooth triangle, okay? And that's periodic, so it repeats all over the place, right? Now this signal, this is how it looks in time domain, and it is a periodic signal. I can represent this signal using something called the Fourier series. And the Fourier series says that x of t, my signal, is equal to the summation from n equals 0 up to infinity, an cosine n omega t, right? And that omega, we call it the fundamental frequency, omega f, omega 1, whatever you like to call it, plus bn sine n omega t. right? What does this say? It says that this periodic signal, which has a general shape, but it's just periodic, can be represented as sum of sinusoids, cosine or sine, at different discrete frequencies. So at F, WF, and W, 2WF, 3WF, 4WF, and so on. Why we care about the representation as sinusoids? Because a single sinusoid contains a single frequency component, right? Even though this periodic signal includes many frequency components because it includes sinusoids at different frequencies added together, but a single sinusoid is a single frequency component. This is why this representation is important. So we know that a sine wave that looks like this, assume this is a sine wave, okay? When I look at it in the frequency domain, I will find that versus frequency, it exists only at a single point with some value, right? We call that the delta function because it exists only at a single point, right? And that point is a particular frequency, that omega f, if it's versus omega, okay? So this is any sinusoid has a particular frequency. That frequency is the single frequency contained in it. Doesn't have any other frequency components, okay? And the amplitude here is dependent on the amplitude of the sinusoid. These are those amplitudes that we have here. So basically this one is a sinusoid with certain amplitude, added to it another sinusoid, double frequency, with another amplitude, added to it another sinusoid, triple frequency, with another amplitude, and so on, right? Now when we look at those in frequency, it becomes one here, one next, one next, one next, one next, right? So now we have been able to look at this periodic signal from a frequency domain perspective and see which frequencies it occupies, right? Similarly, if the signal is aperiodic, this thing becomes eventually an integral, and we call that the Fourier transform, right? So again, if I take this and I assume that it's non or aperiodic signal, aperiodic, which is non-periodic يعني, تمام? So in that case, the transform becomes that x in the frequency domain representation of the signal is equal to the integral from minus infinity to infinity, x of t e to the minus j omega t dt, right? So I take that signal, multiplied by, again, this representation, you learned that in your signal systems, can be actually composed into just cosines with some phase shift, or it can be also represented as exponentials, complex exponentials, also another representation, right? Starting from that complex exponential, if you see that your signal becomes more and more aperiodic, so the period becomes larger and larger such that it becomes almost an infinite period, this summation becomes an integral, and you end up with this representation. That says what? Says that if I have this aperiodic signal in time domain, then when I look at it from the frequency domain perspective by doing this calculation, by calculating this, right, I'll end up with a representation, maybe looks like this, right? And here I will be able to see that it finishes approximately at 3 kilohertz or 30 kilohertz, right? Again, multiplied by 2 pi because this is, okay, this is already f, so no need to multiply by 2 pi. And it starts actually at 3 hertz, right? So if I do that transform, I'll be able to look at this signal that goes with respect to time from the other angle of the frequency and see that it occupies only that frequency range. And it has, for example, the highest value at this particular frequency, it has a less value at this particular frequency, and so on. How much of its power or how much of its amplitude is distributed at the different frequencies. خلاص؟ تمام? Again, this background is very important. This is your signals and systems. You studied a whole course around these topics, okay? Another important thing to keep in mind related to the same topic is what we mentioned a little a while ago when we said that if I have this signal which starts at 3 hertz and finishes at 3 kilohertz, right? Looking at it from a frequency domain perspective, it was not really very suitable for an antenna design. And I wanted really to move it up in frequency. How do I do that increase of frequency? The modulation operation that you mentioned is simply multiplying the signal with a cosine function with some carrier value. It's 2 pi fct, right? And this, when you look at this from a frequency domain perspective, this is a time domain multiplication. Okay, when you look at this operation from a frequency domain perspective, you will find that it is equivalent to the signal shifting up, right? This is where it was originally. Maybe this is the center point. And if I look at the new center point, the distance between those two is going to be this carrier value. Okay, so the signal from a frequency domain perspective has been shifted up in frequency. Okay, this one is F minus FC. It shifts up in frequency, right? Remember, when you, again from signals and systems, when you shift the signal up, you represent that by the signal with the argument with the minus sign, because it moves to the right. It moves to the left, it's with a plus sign, right? All these things, you should be fluent in them, okay? So if you need to revise them a little bit, revise them. We're not going to go through these concepts. I just refresh your memory quickly now, but we're not going to go through these concepts as we go in the course, because this has been a full course by itself, okay? Now that is from the signal's point of view. You just need to remember frequency representation, what's shifting up, what's shifting down, what's time domain representation versus frequency domain representation. The other important concept that you need to remember as well is something called the maximum power transfer concept, or sometimes they call it the maximum power transfer theory. Okay, so what's the maximum power transfer? I will put a simple example that explains this from your circuits course. You studied the similar concept also in your electromagnetics course, okay? And we will discuss both of them quickly. So if you have a certain voltage source, typically this voltage source comes, whether you like it or not, it has some non-idealities, so it has some internal resistance, right? It's not pure without an internal resistance, right? Those two components, the source of the voltage, the value of the voltage source and the internal resistance, are things that comes with the equipment. You buy the equipment, this is a 5 voltage source, adapter for example, and someone has measured its internal impedance due to the design and found it to be, for example, 5 ohm, 6 ohm, 10 ohm, whatever, okay? So this is something that you don't control. Now the question is, what is the best load that you can connect here, okay, such that if you calculate the power going through the load, you will find that it is a maximum value?
It should be equal to RS. It should be equal to RS.
Any other answers? Do you agree with the answer? Okay. Yes. So basically, this is called the matching load, right? So if the load is exactly equal to Rs, you calculate the power going through it, you will find that it is the maximum power. If it's any value greater than Rs or smaller than Rs, the total power going through the load is going to be smaller than the value when RL is equal to Rs, right? So for maximum power delivery to load, you need RL equal to Rs. Okay? It's called the matching load. Okay? That's the load that allows you to get the maximum power transfer. Similarly, in electromagnetics, when we deal with wires in electromagnetics, like those wires that we have here, because of the fact that we deal with lengths that are much, much longer compared to the wavelength of the signal going through it, we deal with those wires with a different concept, the concept of transmission lines, right? And when you start thinking of transmission lines, there is a characteristic, something called the characteristic impedance of the transmission line, right? And you have some source here, which is generating some sine wave, and that wave is traveling. Now you stop thinking about signal appears here and appears here instantaneously. It's actually a traveling wave through the transmission line. And then you have some load here, ZL, where the power is delivered to the load, okay? And similarly, the maximum power transfer theory in the case of transmission line says that you will achieve maximum power delivery to the load if ZL is equal to the characteristic impedance of the transmission line, okay? What if it's not?
We add the capacitors or inductors.
No. What will happen if it's not? I'm not saying how do you correct. Exactly. You will encounter reflected waves. Okay. What's bad about reflected waves? Two things. Number one, efficiency-wise, there is part of the power that's not being used by your load, right? That's a waste of power. Or a waste of energy. The second thing is those reflected ones, they get eventually consumed as heat in the source. So your source will start heating up, building up heat. And in RF system design, this will mean that after a few minutes, sometimes after a few seconds, your whole system is going to stop working. And the system is going to be permanently damaged. Because most of those components are very sensitive to reflected power, heat dissipation. They get dissipated where they should not, right? So you end up with a permanent damage to the system. So it's not only that you lose efficiency, but you end up with your system stopping to work anymore, okay? So again, do you remember what was Z node, generally speaking? اللي هي كانت typically represented as ايه؟
Something like
Generally, it was the root of L over C, right? And what was L and C? L and C was the impedance of the sections. Remember, you break your transmission line, so that's the impedance per unit length, the inductance per unit length divided by the capacitance per unit length. Now, for every geometry of the transmission line, you will have an expression for the inductance and capacitance, which is different. So coaxial cable will have an inductance represented in terms of the dimensions, different from the inductance of twisted pair transmission lines, different from what they call the printed circuit transmission lines, parallel line transmission lines, and so on. So each one of those has a representation for L and C, which is the inductance per unit length and the capacitance per unit length, right? It has a representation for each one of those, different in terms of the dimensions, in terms of the geometry and the material, of course, epsilon, naught, and so on, right? And eventually, Z naught was the root of this divided by this. So eventually, you can find Z naught in terms of the geometry of the transmission line. Reality or practically, you buy the transmission line and you are told that this is a 50 ohm transmission line, this is a 75 ohm transmission line, and so on, unless you are the one who's designing it, okay? If you buy it from the market, it's written. If you buy a cable for your satellite or whatever, it will tell you that this is an RF cable with 50 ohm characteristic impedance, okay? When you are designing RF systems, you have to keep in mind that these systems are composed of different elements and each one of them cascaded to the other. Maybe at some point you will have also a cable, and then eventually you will reach something like your antenna. And in order for all this system to be efficient, the main idea is at any point when you look at the impedance here, Z out, should be the same as the impedance that you see from this side, Zn, when you cascade components, right? So if I go to this point as well, whatever I see from here, Z out 2 should be the same as what I see from this side, Zn 2, and so on, right? As you go through, the output impedance from the previous stage collectively has to be exactly the same as the input impedance to the coming stage collectively, right? Now, in order to make this easier and practical, what happens in the market is that if you go and buy those components, you will find that each one of them has an input and output impedance which is 50 ohm. So the port that takes the signal in is 50 ohm, the port that takes the signal out is 50 ohm, so you will find 50, 50, 50, 50 connected to 50, you will still see 50. And then the transmission line will have a characteristic impedance, which is 50. And the antenna designer makes sure that the input impedance to the antenna is also 50, right? If not, then you will have a problem. If you choose components with different input and output impedance from each other, then this system is not going to be efficient and it's going to malfunction after a while because of the heat built up in the different components due to reflections. Okay? If you are designing a component that you want to put into the market, then not only you will focus on what it does to the signal, for example, amplify or whatever, you have to also make sure that from a circuitry point of view, its input impedance and output impedance is 50, so that you can sell it as a standard component into the market. Okay? So that's one important thing. You have to make sure that things are all matched when you are designing an RF chain, whether it's a transmitter chain or the receiver chain. Okay? Any questions? Yes?
Is that why the components are usually very close to each other so that there are no extra impedance due to the wires or transmission lines?
No, I mean, being close to each other is probably because you don't want to encounter losses, because anyways, any transmission line will have some power losses through it,
But
right? It's not ideal. But if you are connecting things that are far from each other, you will still use a transmission line, an RF cable, which is 50 ohm as well, so it will not have to do with matching. It has to do with the fact that these lines are still not ideal. They have some losses inherent into them, okay? Yeah. Any other questions? Okay, so that's one thing, the other concept that we want to talk about. Another important also thing to remember from your electronics course. So remember in your electronics, you studied things like amplifier, right? Filters, right? And okay, so you studied something like amplifiers, filters, and you even studied also the frequency response of different components that you use in your electronics, right? They have a certain operating frequency. If you go beyond that frequency, you didn't study instrumentation, right? صح? You studied this in instrumentation. There is a certain frequency, operating frequency. Outside that, you lose. Anyways, okay. So amplifiers, very simple. An amplifier is a piece of electronic. I don't care what's inside at this stage, right? Where you have some signal with input power Pi, you get the same signal, so it's not distorted, with output power P output, and there is a gain, and the relation says P output is equal to the gain multiplied by P input. That's what an amplifier is doing, right? However, it's doing this under two conditions. Number one, that you are operating in the linear region, right? Linear region of the amplifier. And number two, that you are operating within the frequency range of the amplifier, okay? If you violate one of those two conditions, so any electronic component, including an amplifier, will have some operating frequency range. Within that frequency range, you can assume that from a frequency domain perspective, it has a constant amplitude, right, across that frequency range. After that, it might decay. It might not be passing your signal normally, okay? So if you are within the frequency range and you are within the linear region depends mainly on limits on output power or limits on input power, right? So some amplifiers, they cannot allow an input greater than a certain value, otherwise clipping of the input might happen. Some other amplifiers, they do not allow an output greater than a certain value, otherwise if your output power goes beyond that, your signal is gonna be clipped. That's the simplest effect. Sometimes it doesn't clip, it just gets distorted. So it becomes not linearly amplified. If it's a sine wave, you will see the effect as this. Supposedly, if this is the sine wave and you amplify it linearly, it should look like this, right? But if you have some effect might look like this. So here it goes normally and then somehow it saturates and then goes down. So it's no longer the same shape but amplified. Okay? It's distorted at the upper part. Okay? So that's because you get out of the linear region because of the value of the input or the value of the output. And there is also if you operate outside the frequency range. There is also the concept of a filter. This is amplifier. You know what's a filter, huh? What is a filter?
It's something, it's a piece of electronic that cuts off unwanted frequencies and passes.
Exactly. So it passes a certain range of frequencies and prohibits the other ranges, right? And there are three types, typically, three classifications. Low pass filter operates at lower frequency, right? So starts from 0 up to a certain upper frequency. There is a band pass filter, which operates between F1 and F2, certain range of frequency, which is not completely low or not completely high. And there is a high pass filter, which starts from a certain lower frequency and goes all the way to supposedly infinity. Yani. This is called high pass filter. This is a band pass filter. Now this is how we see them in textbooks. Reality of filter designs is that, for example, if we look at the band pass filter, we will find that it looks like this. So it's not really zero outside and very constant inside. It's with some ripples and some rise time, some fall time, and some ripples even outside. It's the same for any one of those filters, right? And they typically have, I mean, this is even too ideal. Typically, they have even larger slope, smaller slope, okay? So again, you need to just remember these things, okay? And what happens when a signal goes through a filter, and when I'm dealing with the signal and looking at the effect of the filter, I have to look at the signal from the frequency domain because that's much easier, right? It's very difficult to look at the signal from a time domain and figure out what will happen to it when it passes through a filter, okay? So these things also you need. And the systems theory, so if I have a signal in time domain, it gets convolved with the impulse response to get the output, but in frequency domain, I multiply the frequency domain signal with the transfer function of the system to get the output in frequency domain. Okay, so you have to keep these things in mind. They come from signals and systems and electronics as well. You have been through them before. Okay, any questions? Okay, another thing which is very important as well is the propagation. So signal, or not signal in this case, wave propagation. That's something that you have studied to some extent in your electromagnetics, okay, course. So you have to keep in mind, when I have a signal transmitted from a particular source, and you also studied this, many of you took the wireless communication course, I think, the selected topics last semester, right? So when I have a signal propagating from a particular transmit antenna to a particular receive antenna, right? So this is transmit, and this is a receive antenna. If I put a certain power here, call this P input to the transmitter, I should be able to calculate the output power from the receiver side, and this calculation includes some losses that happens in the channel, okay, and it includes something called antenna gains, right, whether for the transmitter or the receiver side, okay. The losses that happens in the channel is dependent on what's the channel model. This course is not focused on modeling the channel, but at least you need to be able to do power budgeting, right? For a given channel, you should be able to calculate PR. So find, power budgeting is basically find PR given PT. So if you know what's the amount of power that is put into the system here, should be able to do your calculations if you are given a particular channel model to find out what's the received power for that transmitted power. Why do we need to do this? Because typically for communication systems to work successfully, there is a minimum threshold on this received power. We will learn later on where does this threshold come from. And if your received power is less than that threshold is dependent on the receiver design, okay? If your received power is less than that threshold, your receiver will not be able to detect any signal, no matter what you do. Put amplifiers, put filters, do whatever. If your received power after the antenna is less than that threshold, do whatever. Get the most expensive device, it will not receive anything, okay? So if this is the case, then a designer of a communication system has to make sure that the input power here going through the transmitter is sufficient to overcome this threshold. Otherwise, the system is not going to function. Okay? We will learn how to calculate the threshold, and the power budgeting stuff is going to be an essential part of that. Okay? This is not really the wave propagation, because we in that representation in wireless communication, the wave equations and all these stuff were actually summarized into a better representation, which is used for losses calculation and power budgeting for the communication system. تمام؟ Any questions يا شباب؟ انتوا نمتوا ولا صحيتوا ولا رحتوا فين؟ لسه بدري والله، احنا ما دخلناش على الساعة 12 ولا حاجة. صباح الخير. طيب فيش أسئلة؟ ما شاء الله، إيه الهدوء ده؟ هيسأل عشان ما تبقاش الدنيا هادية. وأنا وقفت التسجيل ولا شغال التسجيل؟ والله ما عارف، شغال.
For our purposes, so the channel model will be given as just the parameters, and
Yes.
where we just calculate how
You will be given what's called the path loss. يعني هتبقى you will be given يعني in power budgeting you will be given what's the model for the path loss, and then you can just use it to calculate your power. So your actual work is going to be figuring out the threshold so that you can calculate what's needed to be put into. But again, after you figure out the threshold, you need to be able to do the rest of these calculations to figure out this. تمام? But your actual involvement in this course is going to be figuring out this, the minimum value for this.
Okay.
Minimum required value, okay? طيب, I think I'm more or less يعني done with what, yeah, just again, you didn't study, I know that many of you did not study really antennas, so we will go a little bit on the antenna theory as part of this course, because it's important for any RF system designer to know what are the typical characteristics of an antenna, the gain, the beam width, what does it mean for a communication system, right? And for some simple antenna geometries like the dipole antenna, how to actually calculate these things. For more complicated antennas, if you are not an actual specialized antenna designer, you can just buy the antenna and be able just to figure out the data from the specs, right? But even in order to be able to read these specs, we have to go through that material a little bit, okay? That's it, more or less. I don't want to cram you with more information. That's enough for today.